in the past, we've seen what some of the basic functions look like. We know what our parabola looks like, or we know what the square root function looks like. But when we add extra things to the function other than just the basic function, other than just say, let's say y equals x squared, how does that actually change or transform the graph if I say y equals 2x squared? So that's what we're going to take a look at right now on something called transformations. So let's start out with a basic idea. Remember, y here, all our y values are some function of x. For most of these, generically speaking, I'm going to let our function of x just be x squared because we know what that looks like. That's one of our most common graphs. That's just a parabola with the vertex or the bottom piece right there at the origin. Okay. The first type of transformation are called a vertical shift. So how can we get a vertical shift? Now what we mean by vertical shift is take this graph and raise it up or down. Well, if all the y values are given by our function, right, all our y values are given by x squared, I want to change the y values. So a vertical shift is if you take your original function and you add or subtract some value. So here we have of f of x or minus c. So this would be up c or down by c. So if we were to take, say, this graph, and what if I said y is equal to x squared plus 2? Well, that says take this entire graph, the original x squared, and we're going to move it up 2. So if we went up 2 here and drew the exact same picture, that would give us a vertical shift. Now, of course, if we subtract, let's say if we said y is equal to x squared minus 1, that would take our original x squared and shift it down by 1. So if it went down by 1, I'm about to miss, there we go, would look something like that. So if you have a number on the end of the function that's either added or subtracted, that's a vertical shift, shifts it up and down. All right, which means if we have a vertical shift, we probably have a horizontal shift. Right? For a horizontal shift, we're thinking left and right. Well, here we saw a vertical shift. We had to add something to the y value, right? The original y value was the function. If I want to do a horizontal shift, let's go back to our original again. Some room here. So I'm just going to put my original function back up there. If I wanted to move this horizontally, well, I would have to add something to the x value. So to do that, that's a weird looking y. We would take our original function and I would take the x and add something to it, or take the x and subtract something from it. Now, this one's a little bit strange. So basically what we'd be looking at, let's say if I had this, if we had y is equal to x plus 2 squared. Notice all I did is I added a 2 to the x value. Now, your common sense tells you, oh, that would take the original graph, the black one, and move it to the right 2 spaces. Well, your common sense is actually wrong here. Think about it like this. We're taking all the x values and adding 2 to them. So really what you're doing, imagine if you're taking the x-axis and shifting it to the right 2. Well, if I take this whole axis and I move it to the right 2, the graph is really going to the left 2. So it's kind of the backwards from what you would think. So this graph would actually be over here. Right? Again, kind of backwards from what we would think. So if I had y is equal to x minus 1 squared, right? So this is minus 1. You're not going to the left. We're actually going to be going to the right, because now it's like kind of we're taking the whole axis and shifting it this way. The graph would move that way. So if we go over here to 1 and kind of draw ourselves well, that's a crappy looking parabola. Draw yourself a parabola. You can kind of see how these shifts would work. So here, again, we're assuming C is a positive number here. So if we add a number, this is going to go, excuse me, left C, and if we subtract it, it goes right C. All right, so these are our two types of shifts, a vertical shift and a horizontal shift. That can either move the graph left and right or up and down. Right, if we're just adding a number to the end, it's up and down. If we're adding a number in where the X is, that's going to be left and right. All right, let's see. Let's take a look at the next thing that we can do with a graph is a reflection. So again, let's start out with our X squared here, same picture. So this is our y is equal to x squared. Well, to reflect, we're going to take a look at two reflections here. We're either going to reflect this into the x-axis or the y-axis. I'm going to change the picture for the y-axis. So to reflect this into the x-axis, I want this picture to be the mirror image down here. Well, if you think about it, to mirror image this down here, I'm going to change all these y values to the opposite y values. Now, since all the y values are the function itself, a reflection in the x-axis would be the opposite of all those y values. So this is a reflection in the x-axis. So if we were to take a look at, let's go ahead and write it down here. Y is equal to the opposite of x squared. Well, that would be the mirror reflection of that graph heading that way, right? Because we took all the y values, the x values are the same, we're taking all the y values and we're doing the opposite of them. Now to reflect in the, let's put it like this, to reflect in the y-axis, well, visually speaking, would you agree if I reflect this in the y-axis, it's the same thing, so we actually couldn't visually see the difference. So I'm going to change my graph a little bit and write x cubed. Looks something like that. So to reflect in the y-axis, well, I want any x's that were over here to go over here, and any x's that were over here to go over there. So I want all the opposite x's, which means our reflection would be, if we start out with our function, and if we have a negative x in there, that would be a reflection in the y-axis. So if I were to do this, if I were to do y is equal to negative x cubed, this side would go over here, so this side would go this way, and this side would go over there, would go that way. So you see, that's a reflection in the y-axis. Okay, so if you have negatives involved, that's generally going to be a reflection either in the x-axis or the y-axis. Now, all of these, the reflections and the horizontal and vertical shifts, these are generally called rigid transformations. Excuse me, because the basic shape of the graph didn't change. We just moved it either left, right, up, down, or flipped it in some direction. But the kind of thing like it was a metal wire frame, we didn't do anything but just move that frame around a little bit. The next things we're going to take a look at actually change the shape of the graph. And this is either going to be called stretching or narrowing, or it goes by a lot of different names here. It's just the idea is we're going to change the basic shape. So let's call all right, depending on which textbook you happen to be using, they may use slightly different words here. But we can take a graph and we can stretch it or shrink it vertically. Basically, the idea is if you could take the graph and either stretch it this way or squish it this way. That's what we're talking about by doing that. So again, let's start out with our basic function. Y is equal to x squared. We know what that looks like, and we'll just sketch one up there real quick. Well, what would y equals, real quick. What if we took that function and doubled it, so to speak? What if we have y is equal to 2x squared? All right, what did this actually do? Well, our original y values were x squared. Now we doubled all them. So at every x value, the y value would be twice as big. So here the y value is, let's say 0, so that would stay 0. But if our y value here is 1, it would actually be at 2. If our y value is 2, it'd be at 4. So what it does is it actually stretches the graph like that. Because all the y values at that x value are now twice as big. Same idea, just the other way around. If we had like 1/2 x squared, that means all the y values are now half as big as they were before. So the graph is actually kind of like this. Okay, so a number out in front of an original function changes its vertical scaling, so to speak. Now, the way I generally label these is the blue graph here is more narrow than the original, and the red graph is wider than the original. However, this one was stretched vertically, the blue one was stretched vertically, and the red one was shrunk vertically. But I'm gonna call it narrow and wider. So what did we do? If we take our original function and we multiply it by a number. Now here our c is greater than 0, right? Because basically it's positive, right? Because the negative is actually already taken care of up here. If c's out front, if it's a negative, it's actually two things. It's going to be vertical shrinking or scaling and a reflection all put together in one. But here, if this is greater than 0, well, if c is bigger than 1, the graph is more narrow. And if c is a fraction, which means it falls between 0 and 1, it's, that's the word more, not move. It's more wide or wider. Okay, so since we can have vertical shrinking and stretching, we can also have horizontal shrinking and stretching. So instead of taking our graph and stretching it this way, we can actually take our graph and stretch it this way. Bad news is sometimes we can't tell the difference visually. All right, let's start again. Get ourselves just a little bit more room, and I'm gonna call this horizontal stretching or shrinking. All right, let's take a look at our basic graph once again. There's our y equals x squared. All right, the good news here is it's kind of the same kind of pattern here. To get vertical stuff, we multiplied the y values by a number. So to get horizontal stuff, since x is in the horizontal direction, we're going to multiply the x by something. So the formula here, the basic idea, is we start out with some regular function, and then we multiply the x's by a number. Again, the x is greater than 0. How will that affect the original graph? So what if I did this? What if I said y is equal to 2x squared? All right, to actually see this so you can kind of get an idea of what's going to happen here, I'm going to go ahead and simplify this just a little bit here, and I'm going to not write it in blue anymore. Since both of these are joined by multiplication, both of these are squared, so I can actually write this as 4x squared. Now, by writing the 4 out front like this, that actually falls into this case over here, right? We have a number times the original function, right? We have 4 times the original function. Now, since that number now is greater than 1, we know it's going to be more narrow. So it's actually going to look like that. And the exact same reasoning, where the red pen go, if we had a fraction in there, 1/2 x squared, if we simplified that, again, we'd end up with the same case over here, which would actually just make the graph wider. Okay, so it's basically the same idea, but we're going to have to talk about this in a second. So first off, we saw if the number we multiplied on the inside with the x's is greater than 1, the graph is more narrow. And if it's a fraction, which means it falls between 0 and 1, it's more wide or wider. All right, now here's the problem. I'm going to, just to make this graph look a little bit cleaner here, I'm only going to put 2 of them up here. Let me put this, there's our original, y equals x squared, and I'm going to put the blue one back in there. Let's get this out of here because we're not looking at it. All right, so if I just gave you this picture, and I said the black graph is y equals x squared, what happened to the blue graph? And you say, well, the blue graph looks more narrow than the black graph. So if I said, what happened to it? Was that vertical stretching and shrinking or horizontal stretching and shrinking or shrinking? Well, you can't tell the difference, visually at least, because I could have stretched x squared like this, which would be vertical stretching, or I could have taken x squared and squished it together, which would have been horizontal shrinking. So unfortunately, visually you can't tell the difference. You'd have to actually see the equation. All right, let's start out with a few of these. We're just going to see if we can take a look at a function, see what the original function was, and then state all the transformations that has occurred to it. So let's get us some room here. So our directions for the next couple are going to be function and all the transformations. Okay. The directions here are going to say, state the original or parent, some textbooks use the word parent here, state the original function, and then state all the transformations that occurred to it. All right, so let's just start out with a quick little example. So let's say if I had 2x minus 3 squared plus 4. Okay, one of the harder parts is actually the first thing, stating the original function or parent function. How do you actually do that? Well, what I'm getting ready to tell you is not 100% correct. There are times when this messes up, but most of the time this is really easy to do. If you were to take the original equation, what I wrote up here originally, and erase everything that's not an exponent, so basically erase all the numbers. Notice, well, I'm going to erase the 2, 3, and the 4. What do we have left? Well, the only thing we have left is y equals x squared. So that is our parent function. I think I had, what, 2 minus 3 plus 4, I think is what it was. Okay, so to figure out what the original function is, just erase everything that's erase all the numbers that aren't exponents. All right, so what all is happening to this thing? Well, we have 3 numbers up here, so we have at least 3 things occurring. So let's just start at the first thing and move our way here. Since we have a 2 out front, since it's positive, that's only one thing happening. And since this number is greater than 1, we know that this is going to be a vertical stretch, which generally I'm just going to say that it is narrower. There you go, that's the 2. The minus 3 in here. Now, since that number's in there with the x, we know that that is a horizontal shift. So we have a horizontal shift, and that's the negative 3 or minus 3 in there. Now remember, that's the opposite of what you think. So this isn't going to move left 3. This is actually going to go right 3. And the last thing we have here is we're adding a number to the very end. So this is a vertical shift. So that's our plus 4 out there at the end. So this is going to be up 4. Okay, for questions like this though, all you really need to do is say the graph is narrower, it's moved right 3 and up 4. So let's try another one. I'm gonna put it down here. So let's say we have y is equal to negative square root x plus 5 minus 3. All right, first off, what is the original? Well, the original is going to be, if we come up here and we erase all the numbers, so I'd erase the -1, the 5, and the -3, you'd see all we have left is the square root of x. So that's what our basic function looks like. So what does the rest of the stuff up here do? Well, the negative out front, the negative here, I'll do it in red, you don't need to write that, that's a reflection in the x-axis. The plus 5 is going to give us left 5, and the minus 3 are just going to be down 3. So if we started with this original graph, which we're supposed to know what it looks like right now, we could apply these transformations and get what this graph looks like, which is kind of nice because our basic graphs are very easy to graph, and then all we gotta know is, okay, well, that's how it is shifted around. All right, let me give you a little bit more room. I want you to try one of these. Let's go that out of there. So a little bit harder. So let's say I got y is equal to -1/2 plus 2 minus 3. All right, do me a favor, pause the video and see if you can stay what the original function is and all the transformations. All right, if you're back, let's see how you did. Now again, I'm just gonna kind of write it up above. Since we have a -1/2 out there, there's actually two pieces. We have a negative and a half. The negative out front is a reflection, and that's our reflection in the x-axis. The 1/2 is a multiple out front. Now, since that's a fraction, that's going to make the graph wider. Oh, I forgot to say what the original function was. I'll do it down here. That means our function is going to be wider. The plus 2 in there with the x, that's going to be left 2. And the minus 3 out there is going to be down 3. Now, what I should have done in the first part, which I forgot, what is our original function? Well, again, if you take this and you erase all the numbers that aren't exponents, the only thing you end up with is the absolute value of x. Now, again, we know what this shape looks like. This is just a V. So what's happening to that V? It's reflected in the x-axis. It's a wider V than it used to be. It's going to be left 2 and down 3 from where it started at. All right, now, it would be nice that we could do these transformations in any order that we wanted to, like reflected, wider, but there is actually an order that you have to apply the transformations to get the correct result. So, order to apply the transformations to a graph. Now, if the question just says, you know, what happened to the graph, then you did, this is perfect. Those are all the transformations. But if you're actually going to take your absolute value of x and apply all these transformations, you have to do it in a specific order. The first thing you have to do is any horizontal shifts that it might have. Step 2, any stretching or shrinking, so that's either vertical stretching or horizontal stretching or shrinking, either one of those. Then once you apply that, next thing you need to do is any reflections. And the last thing, the only thing we have left, vertical shifts. Okay, so if you are applying these transformations to a graph, these are the order that they have to be applied. Take the graph, shift it horizontally, then make it wider or skinnier if that applies. Do any reflections either on the x-axis or the y-axis, and then shift it either up or down. All right, knowing what a basic graph looks like and then what the transformations are can be really, really helpful in the future when we're analyzing graphs to to look for other features of them. So really, really useful stuff.